All right, kiddos. In this video, we're going to jump from the unit circle to what we call SohCahToa. And we're going to get out of the unit circle, and we're now going to consider any old right triangle and see what happens based on what we know about sine and cosine, right? So far, we kind of think of sine and cosine as being either sides of this reference triangle or either the x or y value of the terminal point, right? So we're in the unit circle. There's our hypotenuse / radius of 1. Theta is the angle of rotation, and then cosine is the base or the x value of the terminal point. Sine is the height or the y value of the terminal point. Right? So that much you guys are doing a great job with. So let's jump, however, outside of the unit circle. And just for argument's sake, I'll make a larger triangle, but I'm going to make it a right triangle, and I'm going to preserve that same angle theta. Right? So theta, 90, 90. Right, so you're probably thinking to yourself, wow, those triangles are going to be similar by angle. Theta congruent to theta, 90 congruent to 90. So those triangles are indeed similar, right? And because they're similar, we can set up proportions because we know that corresponding sides of similar triangles are proportional, right? So before we start setting up proportions, I have to come up with names for the three sides of this triangle, right? And the names of this triangle have everything to do with, or they're relative to this theta. We call this theta the reference angle, same as that reference angle there, right? Now, the side opposite the theta, the reference angle, we call O. O for opposite. Opposite what? It's opposite this reference angle theta, okay? The side across from 90 we call H for hypotenuse because it's the hypotenuse. No matter what reference angle we use, this will always be the largest side of that right triangle. The remaining side we call A, adjacent. Okay? And so we now have names for those three sides, and those names are relative to the reference angle theta. If theta moves over here, this now becomes the opposite side, and this becomes the adjacent. Okay? And we always use theta as one of the two non-right angles. Okay? So now, now what we're going to do is we're going to set up some proportions, okay? Because we have names for the sides in this larger similar triangle, and we already have names for the sides of the smaller unit circle triangle, okay? So watch what happens. It's fascinating, right? I can say that the ratio of, now follow here, base to hypotenuse is equal to base to hypotenuse, right? Base of the triangle to hypotenuse equals base of this triangle to hypotenuse, right? Or I could say the height to hypotenuse equals height to hypotenuse, okay? So let's see what happens, right? So I'm going to set up the ratio on using the left unit circle triangle, the sine of theta over 1, right? Base over hypotenuse, and that has to be equal to, because corresponding parts of similar triangles are proportional, parts being the sides. So sine to 1 is equal to O to H. And of course, I can just write that as sine of theta, because I don't have to write over 1, it's still sine of theta, equals opposite over hypotenuse. Okay? Now I'm going to put a big old box around that. Okay, the other proportion I could set up has to do with a cosine, right? I could say cosine over 1 on the unit circle triangle, cosine over 1 would be equal to the ratio of what? That's right, A over H. Right? Because these two triangles are similar, then their corresponding sides have to be proportional. Cosine over 1, therefore, equals adjacent over hypotenuse. Right? So cosine of theta over 1 equals adjacent side over hypotenuse, which I can also just write as cosine theta equals A over H. Okay, and again, that's just a proportion that I can create from the two similar triangles, because corresponding sides have to be proportional. Right? Now, the third, to round it off, I can say the tangent of theta is really equal to sine over cosine, right? By definition of tangent. And now the sine of theta, which I have right here, is over H. Over H, that's a sine of theta. Oh, and the cosine of theta on the bottom is a over h, right? And we're trying to figure out what the heck that means, right? So when I divide by a fraction, I multiply by the reciprocal of the denominator. The h's cancel, and I just am left with O over A. I'm running out of room. Sorry. Right? So I'm going to write that a little cleaner up here. Tangent of theta equals opposite over adjacent. Tangent of theta equals opposite over adjacent. Okay? So those three relationships, sine of an angle, cosine of an angle, tangent of an angle, now pertain to any triangle as long as it's right, not just the unit circle. Okay? And this we affectionately refer to as SO. And the SO part reminds us that sine equals the opposite over hypotenuse. Ka, and the ka part reminds us that cosine C equals adjacent over hypotenuse. Toa. And the toa part reminds us that the tangent T is equal to opposite over adjacent of any right triangle. Okay? So how might that be helpful? Well, let me give you a specific problem. Okay? This allows us to solve any right triangle as long as we know a side, right? So let's just assume we have this triangle here. And let's say that the reference angle here is 18 degrees. And let's say that the hypotenuse is 10. I want to find that side. Now, if that reference angle were 30, we could use 30, 60, 90 ratios. If it were 45, we could use 45, 45, 90 ratios. If we knew another side and we're trying to find the third, we can use the Pythagorean theorem. We just can't. But what we can use, comma, however, comma is trig. So here's how it works. I'm going to identify my reference angle. Based on that reference angle, and I can use 18, or I could, if I wanted to, use 72 up here. But I'm going to stick with 18. Then the side I'm looking for is called, that's correct, opposite, O. The side I know, 10, is, that's correct, hypotenuse. And now I'm going to go back to, okay, well, which of the three ratios can I use, right? So I'm looking for O, and I have H. So I'm looking for O, and I have H. The sine has an O and an H in it. So I'm going to set up the following equation. Based on SO of SohCahToa. Sine of the angle theta is equal to the ratio of opposite to hypotenuse of that right triangle. Right? Now I'm just going to fill in numbers. 18 is my angle. It's in degrees. Opposite is what I'm looking for, and hypotenuse is 10. Right? So there I have a little equation. Right? And there's only one variable, x. Therefore I can solve for that variable. And the way I solve for that variable is by multiplying, in this case, both sides by 10. Right? And you now may be asking, well, what on earth is a sine of 18 degrees? Well, let's ask our calculator. So now is when we return to our calculators and say, calculators, help us out, right? So in our calculator, we will press 10 times sine of 18. So we're going to begin to use more and more of our calculators once it pops up. Okay? So in my calculator, once it pops up, it's thinking a little bit, I'm going to write 10 sine of 18 degrees. Come on, calc, help a brother out. Come on, man. Still thinking. Okay, maybe you guys can do this right now. For some reason, mine is not working. I apologize for that. Okay, so at home, just press 10 times sine. Gosh, what's happening? Press 10 sine of 18 degrees, and that will be your solution. Okay, let's see if we can get it up on Sketchpad. Sorry about this. Yeah, let's just forget. You can do that at home, right? So press that in your calculator, and that will be this side here. Okay, we'll work with more of these problems tomorrow. Sorry for the glitch. See you tomorrow.